Everyone knows the big boy. Everyone's heard of the Flying Scotsman. But in 1932, a machine rolled out of Baldwin Locomotive Works that engineers said would tear itself apart on the first curve. They called it a mechanical impossibility, a violation of physics, a 400-ton suicide machine. Instead, it set 4 world records in a single year. The locomotive was the Pennsylvania Railroad's S1 experimental duplex, though that designation came later after the concept proved itself. The prototype that preceded it, the one that actually broke the records, carried a different number, 6446. 6 pilot wheels, 4 drivers, 4 more drivers, 6 trailing wheels, 20 wheels supporting a boiler longer than most entire locomotives. Critics looked at the blueprints and saw catastrophe. The rigid wheelbase alone violated every principle of locomotive design, established over a century of steam engineering. The driving wheels were divided into 2 separate engine units under a single rigid frame, with the front unit's cylinders driving the second set of drivers and the rear unit's cylinders driving the third set. No one had ever attempted anything like it at this scale. The Pennsylvania Railroad didn't care what conventional wisdom said. They had a problem that couldn't be solved with conventional locomotives. By 1930, the railroad's flagship passenger trains faced a crisis of speed. The Broadway Limited and other premier services were losing ground to emerging competition, not from other railroads, but from the promise of faster technologies on the horizon. Passengers were beginning to talk about airplanes. The railroad needed trains that could sustain 100 miles per hour for extended distances, not just hit that speed on favorable gradients for a few minutes of glory. They needed locomotives that could maintain that pace while hauling 12 to 15 heavyweight passenger cars across the rolling terrain of Pennsylvania and Ohio. Traditional steam locomotives hit a fundamental wall at high speeds. The problem wasn't power, it was mechanics. The reciprocating mass of pistons, rods, and valve gear created what engineers called hammer blow, vertical forces that pounded the rails with every stroke. At low speeds, this was manageable. At 80 miles per hour and beyond, it became destructive. The faster a conventional locomotive ran, the more violently it hammered the track, and that hammer blow increased exponentially with speed. In the driving wheels themselves became unbalanced flywheels, generating forces that threatened to shake the machine apart. The Pennsylvania Railroad's solution was radical: split the driving force between 2 separate engine units, reducing the reciprocating mass per unit, and theoretically cutting the hammer blow in half. But this created another problem. Most high-speed locomotives used large driving wheels, 80 inches in diameter or more, to cover distance with each revolution. The 6446's design required 4 separate sets of coupled drivers under one rigid frame. Making those drivers large enough for high-speed work while maintaining adequate boiler capacity meant creating a locomotive longer than anything that had successfully negotiated American railroad curves. In the wheelbase from the front of the leading truck to the rear of the trailing truck measured 77 feet. The rigid wheelbase, the distance between fixed axles that couldn't swivel independently, exceeded 40 feet. Engineers calculated that this configuration would bind on curves, forcing the drivers to skid rather than roll. The flanges would climb the rails. The locomotive would derail. Baldwin built it anyway. The prototype emerged in November 1932. It weighed 389 tons without its tender, heavier than 2 conventional passenger locomotives combined. The boiler operated at 300 pounds per square inch, feeding 4 22-inch cylinders with a 26-inch stroke. The drivers measured 84 inches in diameter, massive even by passenger locomotive standards. Every dimension pushed boundaries. The firebox consumed coal at a rate that made veteran firemen stare in disbelief during early tests. The first trials happened on straight track. The locomotive moved, though critics noted this proved nothing. Straight-line operation had never been in doubt. The question was what would happen on curves, particularly the tight industrial trackage and branch lines that any truly versatile locomotive would need to navigate. They took it to Horseshoe Curve. Horseshoe Curve, west of Altoona, Pennsylvania, represented one of the Pennsylvania Railroad's most challenging pieces of engineering, a sweeping bend that allowed the main line to gain elevation through the Allegheny Mountains. The curve itself measured 220 feet in radius on the inner rail, tight enough to test any locomotive's tracking ability. If the 6446 bound on Horseshoe Curve, it would bind anywhere. The locomotive negotiated the curve without incident. Observers noted that the divided drive system actually helped rather than hindered. The 2 separate engine units articulated slightly under the main frame, allowing the driving wheels to find their natural path through the curve. What looked like a rigid mechanical nightmare on paper demonstrated unexpected flexibility in practice. But navigating curves, even difficult ones, wasn't the point. The Pennsylvania Railroad needed speed, and speed meant testing on the kind of long, fast runs that would reveal whether the prototype could actually deliver on its promise. In January 1933, the railroad scheduled a series of dynamometer car tests, runs with sophisticated instrumentation to measure every aspect of the locomotive's performance. The test trains ran between Chicago and Fort Wayne, Indiana, a relatively flat section that allowed for sustained high-speed operation. Engineers attached recording devices that would track speed, drawbar pull, coal consumption, water use, and steam pressure throughout each run. The first record fell on January 15th. Hauling 12 passenger cars weighing 1,020 tons, the prototype sustained 102 miles per hour for 68 consecutive miles. Not a brief sprint, 68 miles at better than 100 miles per hour with a 1,000-ton train. No steam locomotive in regular service had ever maintained that speed for that distance under load. The dynamometer recordings showed steady drawbar pull throughout the run, with boiler pressure remaining stable despite the massive demand for steam. The second record came 9 days later. Same route, but with a lighter train, 8 cars totaling 680 tons. The locomotive reached 115 miles per hour and held that speed for 22 miles. At certain moments, it touched 120 miles per hour, though those peaks lasted only seconds. The sustained 115 mile per hour average represented a new benchmark. For comparison, the famous British locomotive Mallard wouldn't claim its 126 mile per hour world record for another 5 years, and that record represented a brief peak during a carefully staged run, not sustained operation with a revenue-grade passenger consist. The third record addressed efficiency. Critics had assumed the massive locomotive would consume coal and water at ruinous rates, making it economically impractical despite its speed. The dynamometer tests revealed something different. At 100 miles per hour with a 1,000-ton train, and the prototype burned 13,600 pounds of coal per hour, certainly substantial, but not dramatically worse than two conventional locomotives hauling the same train at 70 miles per hour. The key metric was coal per ton-mile, and there the 6446 proved surprisingly economical. It moved more tonnage faster while consuming less fuel per unit of work performed. The fourth record was the most telling. Traditional high-speed locomotives needed special conditions, perfect track, favorable weather, light trains. The prototype demonstrated consistent performance across varying conditions. It hauled heavy trains in winter weather, maintained schedules despite wind and rain, and proved capable of rapid acceleration from station stops, critical for passenger service with frequent intermediate stops. During one test run, it accelerated a 12-car train from a standing start to 60 miles per hour in 90 seconds. Conventional passenger locomotives needed nearly twice that time with similar loads. The Pennsylvania Railroad had proven the concept. The 6446 wasn't a fragile record chaser. It was a practical, reliable machine capable of revolutionizing passenger service. And then they stopped. The railroad filed the test reports, shelved the prototype for several years, and continued operating conventional locomotives on their premier trains. When they finally did build a production duplex locomotive, it came nearly a decade later, the T1 class of 1942, and even those remarkable machines served for less than a decade before dieselization swept steam from American railroads entirely. Why? If the prototype performed so brilliantly, why didn't the Pennsylvania Railroad immediately build a fleet? The answer lies in what happened between 1933 and 1942. The Great Depression crushed railroad traffic. Passenger numbers plummeted. The Pennsylvania Railroad, like every other American railroad, fought for survival rather than innovation. Capital for new locomotive construction vanished. The experimental 6446, impressive as it was, required significant investment to develop into a production design. The railroad couldn't justify that investment when trains ran half empty and revenue collapsed. By the time the economy recovered and wartime traffic created urgent demand for high-speed passenger power, nearly a decade had passed. The original prototype had been cannibalized for parts. The engineers who developed it had retired or moved to other projects. The Pennsylvania Railroad essentially started from scratch with the T1 class, incorporating some lessons from the 6446, but also introducing new complications that limited the T1's ultimate success. The tragedy is what might have been. If the 6446 had entered production in 1933, American passenger rail service in the late 1930s would have looked dramatically different. Sustained 100-mile-per-hour operation with heavy trains would have been standard on major routes. The Pennsylvania Railroad's Broadway Limited could have covered the distance between New York and Chicago in under 12 hours, a schedule not achieved by rail until Amtrak's modern high-speed Acela service, using electric power and upgraded track more than 60 years later. The locomotive's 4 world records, sustained high-speed operation, peak velocity with load, either efficiency at speed and acceleration capacity, represented achievements that other railroads and other countries studied intensely. German and French railway engineers examined the Pennsylvania Railroad's test reports. British designers looked at the duplex concept for their own high-speed projects. The influence spread far beyond American borders, but the machine itself remains largely forgotten. Ask most railway enthusiasts about Pennsylvania Railroad passenger locomotives, and they'll mention the GG1 electric locomotive or the K4S Pacific, both iconic designs that served for decades. The 6446 experimental duplex rarely appears in histories. Its records are footnotes. The locomotive that proved engineers wrong, that set benchmarks other nations studied, that demonstrated steam technology could compete with emerging diesel power on speed, if not on economics. This machine exists now mainly in technical papers and test reports archived in railway museums. The engineers who said it would derail were wrong. The locomotive that shouldn't have worked revolutionized thinking about high-speed steam operation. It set 4 world records in a single year and proved that unconventional designs could deliver extraordinary performance. History chose to remember other machines, locomotives that looked more traditional, that served longer, that fit more comfortably into established narratives about how steam technology evolved. The 6446 was too radical, too brief, too perfectly timed with economic catastrophe to secure the legacy its performance deserved. But the records remain. A4 benchmarks set in 1933, most of them unmatched by steam locomotives anywhere in the world for years afterward. And somewhere in the archives, the dynamometer charts still show those sustained 100-mile-per-hour runs, proof that engineers could be spectacularly wrong and that impossible machines could rewrite the rules of what steam power could achieve.